Next to the speed with which a computer performs its basic functions of adding, subtracting, multiplying, dividing, and comparing values, there is no other measure more revealing than its capacity to store, then recall on command, the information contained within the systems. In this video, you will examine several important concepts behind semiconductor memory devices. You will learn about the basic technologies used, memory organization and configuration, as well as design considerations. Semiconductor memory devices may be classified in one or two basic categories, permanent or temporary. As you will see, both have similar properties, yet each plays a different role and each has unique advantages and disadvantages. You will examine both permanent and temporary memory devices in this video. We will begin by examining permanent devices first. As the name might suggest, permanent memory devices are capable of retaining information at all times, even if power is removed from the system. Permanent memory is said to be non-volatile and is used to store fixed program instructions which will not change during the life of the product. As you can see, there are four basic types of permanent memory devices. They are ROM, which stands for read-only memory, PROM, which stands for programmable read-only memory, EPROM, which is erasable programmable read-only memory, and the EEPROM, which is electrically erasable programmable read-only memory. We will examine these devices one at a time. Let's begin with the ROM, or read-only memory, since it's the oldest and most straightforward of the permanent semiconductor memory devices. The data contained within a read-only memory device is usually specified by the customer. The IC is then manufactured to contain this data. Once it has been manufactured, it can never be altered. In order to change the information contained within the ROM device, a new IC must be manufactured, then substituted for the old one. Since this is a time-consuming and expensive process, the read-only memory device is economically feasible only when used in large volumes for a thoroughly debugged application. To understand how the read-only memory device works, we will examine this simple circuit diagram of a 16-bit ROM which uses diode elements. At first glance, this circuit may look somewhat complicated, but in reality, its operation is very simple. You should have noticed there are two decoder circuits used in this ROM device. One is used for the columns and one is used for the rows. The control circuitry used for the ROM devices is designed to read one row at a time and one column at a time for each row. We will now examine the operation of this simple circuit. When row 00 and column 00 is scanned, the current will flow through from ground through resistor R1, through transistor Q1, through diode D1, through resistor R2, then to B+. The value of resistor R2 will be much greater than resistor R1, therefore the majority of the voltage drop will be placed across resistor R2. This places the bottom of R2 close to ground potential, therefore a low is being produced at the output. Next, row 00, column 01 is scanned. Since column 01 has a diode connecting the column decoder to transistor Q1's collector, the current now has two paths with which to flow. Since the forward resistance of the selected diode is much less than that of diode D1 and resistor R2, most of the current will flow through the selected diode. This results in less current flowing through resistor R2, which in turn causes the voltage drop across R2 to decrease. This, in effect, causes the output to become closer to the B+ potential, which results in a high at the output. This sequence will continue throughout the entire ROM device. First a row is selected, then the columns are selected one at a time. Every time a diode is placed between the row device and the column decoder, the current will flow through the selected diode, causing the output to go high. In the same respect, when there is no diode connecting the row to the column, then the current will flow through resistor R2, which will result in the bottom of R2 being brought closer to the ground potential, thus producing a low at the output. Even though this simple circuit has only one output, its basic operating principle remains the same regardless of the number of outputs. Read-only memory devices are available in both TTL and MOS configurations. Here you see a block diagram of a 4096-bit read-only memory device, which is organized in a 512-word by 8-bit memory configuration. Notice that it contains the row and column decoder sections, an address input buffer, an output driver stage, and a 512-word by 8-bit memory section. The output of the device is enabled by applying a logic high to the chip enable input. Some manufacturers refer to the chip enable input as the chip select or the output enable input. To read the information contained at a particular location in the ROM device, the 10-bit pattern address must be placed into the address input buffer section. Then the chip enable input is brought high, which causes the data stored at the specified address to be output via the IC's output pins, which are labeled D0 through D7. The data then travels along the data bus to the microprocessor. Typical access time for such read operations is approximately 15 to 80 nanoseconds for most TTL ROM devices. When the chip enable input returns to its low state, the outputs become disabled, and the output line returns to a high impedance state, which effectively disconnects the ROM device from the data bus. We will now pause for a brief review of the material just discussed. The data contained within the read-only memory device must be constructed within the device by the manufacturer. Once the ROM is fabricated, the information contained within the device cannot be altered. In order to change the data, a new device must be manufactured. The typical access time for a read operation of a TTL ROM device is approximately 15 to 80 nanoseconds. There are two basic types of memory devices, permanent and temporary. The ROM is a permanent type memory storage device. Read-only memory devices are commonly available in both TTL and MOS configurations. The chip enable input is oftentimes referred to as a chip select or output enable input. To read information from a ROM device, the address must be selected and the enable input must be activated. This concludes review number 1. Next, we will examine the PROM device. The programmable read-only memory device offers one major advantage over the ROM device in that it can be programmed by the end user. But like the ROM device, once it is programmed, it cannot be changed. The memory configuration of a programmable read-only memory device is very similar to its counterpart, the ROM. The primary differences are that each bit contained within a PROM device is manufactured to represent a high output. Another difference is that during the construction of the PROM device, each connecting diode contained within the memory array will have a thinner layer of conducting material attached to it. This thin layer acts as a fuse link, which will open to produce a low state when the device is programmed. A factory-fresh PROM can be programmed with a PROM burner. The PROM burner is a specialized piece of equipment designed to generate high-energy pulses which destroy the desired links to match the contents of the user's data file. Programming the PROM is a very simple process. First, an address is selected by activating the desired row and column lines. Then a jolt of high energy is applied at the desired address. This causes the thin layer of conducting material to burn open. When this occurs, it permanently opens the circuit between the row lines and the column lines. This same procedure is performed at each data address until the entire PROM device has been programmed. While the device is being programmed, the outputs are generally disabled. Here you see the PROM burner connected to a typical programmable read-only memory device. As you will notice, the PROM burner was connected to the outputs of the PROM device. Also notice that there are two memory-enable inputs on this device. One is labeled ME1 and the other is labeled ME2. When the PROM is being programmed, either ME1 or ME2, or in some situations both ME1 and ME2, must be brought high. As was stated earlier, when the PROM device is manufactured, it contains a high at all addresses. Therefore, the logic lows must be programmed into the device. To program a logic 0, the following procedure is generally followed. First, a voltage of 5 volts must be applied to the VCC input. Next, select the word to be programmed using address inputs A0 to A7. Third, apply a logic 1 to either or both of the enable inputs. In this example, we applied a high at both enable inputs. Fourth, apply the high energy programming pulse to the outputs where the low bit levels are desired. Next, advance to the next output and or word, programming only one bit at a time. This sequence is continued until the entire PROM device has been programmed. This procedure is a basic process used to program PROM devices. However, when programming a given PROM device, it is recommended that you follow the manufacturer's guidelines. To verify that the PROM device has been programmed, apply a logic 0 to both of the enable inputs, then check for a low output at the desired address. Programmable read-only memory devices are slightly more expensive than ROM devices, but their flexibility often justifies the higher cost. We will now pause for a short review of the programmable read-only memory device. The programmable read-only memory device offers a tremendous advantage over the ROM in that it can be programmed by the end user. The PROM can be burned or programmed only once. Once programmed, it cannot be erased. To program the PROM, a special piece of equipment is used. It is called a PROM burner. The factory fresh PROM consists of a matrix of fusible links. An intact link produces a binary 1, whereas an open link produces a binary 0. PROMs are programmed one bit at a time. This concludes review number 2. Next, we will examine the EEPROM. The EEPROM, or Erasable Programmable Read-Only Memory Device, has been the preferred method of permanent storage of data in single-board computers. This is due to the fact that it overcomes the major disadvantage of the PROM device, its inability to be programmed more than once. Modern EEPROMs can typically be programmed and erased and reprogrammed hundreds of times and still maintain reliability. Here you see a typical memory cell in an EEPROM device. Notice that it uses metal oxide semiconductor, MOS, technology. The EEPROM memory cells contain a floating gate. The floating gates are small semiconducting regions placed between two metal levels. This, in effect, places a capacitance within the device. The electrical characteristics of the floating gate are carefully selected so that its polarity is not affected by the normal plus 5 volt operating conditions. An EEPROM will contain a matrix of these special MOS transistors. To better understand how the EEPROM is capable of storing information using MOS technology, we will examine this simple circuit. To start with, a factory-fresh EEPROM will contain a high at all memory addresses. Therefore, when the EEPROM is programmed, the high bit is converted to a low. When a positive 5 volts is applied to this simple circuit, we see that the current flows from ground through resistor R1 and into the drain of the MOS device. As you recall from your semiconductor theory on MOS devices, the gate must have a positive potential applied before a current will flow between the drain and source. The floating gate in this MOS device will prohibit the main gate from affecting the conductivity of the transistor. This results in the transistor remaining off. Therefore, only a very small amount of current, made up primarily of minority charge carriers, will flow through the device. This very small current flow then proceeds out the source into resistor R2, then into the positive side of the power source. Since the majority of the voltage is being dropped across the MOS device, and the output is being taken from the source lead, then the output of the device will become a high. Now let's assume that the MOS device has been programmed to store logic 0. As you can see, the floating gate within the MOS device has become charged. We will see how this happened in a few minutes. When the positive 5 volts is applied to the circuit, the current will flow through resistor R1, then through the MOS device from the drain to the source, then through resistor R2, and then to the positive side of the power source. As you notice, the current was able to flow through the MOS transistor due to the charge being applied at the floating gate. In effect, the floating gate biased the transistor on, allowing the current to flow. Since the transistor is biased on, its resistance drops to a very low value, which results in the majority of the voltage being dropped across resistor R2. This causes the bottom of resistor R2 to effectively be placed at ground potential. Since the bottom of resistor R2 is placed near ground potential, so is the output, which results in the output becoming low. As you can see, by placing a charge on the floating gate, we have succeeded in storing a logic 0 in this memory cell. Now let's see how this cell is programmed. Programming an EEPROM is very similar to programming a standard PROM device, with this exception. The EEPROM is not burned, it is charged. A special EEPROM programmer is used to select the desired address to be programmed. Then it places the desired binary information at the control gate of the device. The EEPROM is then pulsed with a high energy pulse, which locks the bit information into the substrate of the chip. The bit of information is stored in the floating gate, where it remains even after programming voltages are removed. To erase an EEPROM, it is necessary to remove the charge stored on the floating gate of the device. This is accomplished through the use of ultraviolet light energy. Since light energy is used to erase the data stored in an EEPROM, most EEPROM devices will have a transparent window that permits the memory circuits to be exposed to the ultraviolet energy. When the ultraviolet energy is exposed to the memory elements, the short wavelength of the UV light causes the molecules to become excited and randomly move within the substrate. This allows the stored charge to dissipate. Gradually, the IC will return to its pre-programmed state. It takes an average of 15 to 30 minutes of exposure to a concentrated ultraviolet light source to erase an EEPROM. After an EEPROM has been programmed, it is recommended that you place an opaque material over the transparent window of the device. This is necessary because common sources of light, such as sunlight, room fluorescent lights, and blacklight, may contain enough ultraviolet energy to trigger random charge dissipation, which will introduce errors into the device. It is possible to store multiple programs in a single EEPROM IC, providing, of course, each program is stored at a different address. Also, the entire EEPROM does not have to be programmed at once. However, once a bit has been programmed to a 0 or low, it cannot be changed back to a 1 or high unless the entire IC has been erased. Here you see the pinout for the Texas Instrument TMS27C64, which is a typical CMOS EEPROM IC. This chip is referred to as a 64K EEPROM since it is capable of storing 8,192 8-bit words, which is approximately 64,000 bits. The TMS27C64 has 13 address inputs labeled A0 through A12, 8 data input outputs labeled Q1 through Q8, and 3 control inputs labeled not PGM for program, not G for output enable, and not E for chip enable. This IC also contains 2 power supply pins. VCC is plus 5 volts, and VPP is plus 5 volts for normal read operations and 12.5 volts for programming operations. Reading data from the TMS27C64 is a very simple process. First, the program input, not PGM, is brought high and plus 5 volts is placed at the power supply pin VPP. Next, address inputs A0 through A12 are used to select the desired address. Then the chip enable input, not E, and the output enable input, not G, are brought low. After a short delay, the data stored at the selected address will be displayed at outputs Q1 through Q8. Programming this EEPROM is also a very simple process, but keep in mind programming can only change ones to zeros. It cannot change zeros to ones. Therefore, before the EEPROM can be programmed, its memory addresses must all be changed to ones by exposing the EEPROM's transparent window to a concentrated ultraviolet energy. The first step in programming this IC is to select the desired address to which the data will be placed. Remember, the address lines are A0 through A12. Next, the desired data to be programmed at this address is placed at inputs Q1 through Q8. As you recall, inputs Q1 through Q8 are used for both input and output operations. Next, the power supply pin VPP is increased to its programming voltage of plus 12.5 volts. Then the chip enable input, not E, is brought low. Next, the program input pin, not PGM, is pulsed low for approximately 50 milliseconds. To verify that the byte has been programmed, simply bring the output enable input, not G, low, and the programmed data should appear on Q1 through Q8 for the programmed address. A word of caution: not all EEPROMs are erasable. There are one-time programmable EEPROMs available on the market. These use EEPROM technology but have no windows and therefore are not erasable. We will now pause for a short review of the material most recently discussed. The typical EEPROM can be written to and erased from several hundred times and still maintain its reliability. The EEPROM memory cell contains a floating gate which is used to store a 0 when charged and a 1 when not charged. The EEPROM memory cell is programmed by forcing a high energy state through the floating gate. The gate will retain this charge even after the programming voltage has been removed. Most EEPROMs contain a transparent window which is used to permit ultraviolet energy into the memory section. This ultraviolet energy will erase the data contained within the IC. An opaque label is generally placed on the transparent window of the programmed EEPROM to prevent outside sources of ultraviolet energy from entering the memory section of the IC and causing errors in the data. Once a bit has been programmed to a 0, it cannot be changed to a 1 without erasing the entire IC and starting over. This concludes review number 3. We will now examine the electrically erasable programmable read-only memory device. The EEPROM, or as just mentioned, electrically erasable programmable read-only memory device, is a popular alternative to the EEPROM just discussed. As you recall, the major disadvantage to the EEPROM was its inability to be reprogrammed quickly. This was due to the fact that the EEPROM had to be subjected to a concentrated ultraviolet light source for a period of 15 to 30 minutes before the data was erased. In regard to reprogramming the EEPROM, it was an all or nothing process. You either erased all of the data or none at all. The EEPROM, on the other hand, can be erased and reprogrammed in a matter of microseconds. And an equally important advantage is the fact that the EEPROM can erase 1 byte at a time instead of the all or nothing approach. Here you see a pinout for the Texas Instruments TMS-28C64, which is a CMOS 64K EEPROM. This memory device uses a floating gate technology similar to that used by an EEPROM. This EEPROM is capable of storing 8,192 bytes of information. The TMS-28C64 has 13 address inputs labeled A0 through A12. It also has 8 data input-output pins labeled DQ0 through DQ7. The control pins on this device are not W for write, not G for the output enable, not E for the chip enable, and R, not B for the ready busy signal. Reading information from the EEPROM is a simple process. First, the address is selected using the address inputs A0 through A12. Next, the write input not W is brought high, while the output enable not G and the chip select not E are brought low. After a short delay, the information placed at the selected address will appear at output pins DQ0 through DQ7. Writing to the EEPROM is also a very simple process. Writing a single byte can take as long as 10 milliseconds, which is a considerable length of time in the microprocessor world. However, once the write cycle is initiated, the EEPROM will take over and complete the process on its own. This allows the microprocessor time to perform other tasks. The EEPROM cannot be read or written to until the write operation is complete. To program the EEPROM, you must first select the desired address to which the information is to be placed using address inputs A0 through A12. Next, the chip enable input not E and the write input not W are brought low. Also at the same time, the output enable pin not G is brought high. Third, the data to be stored is placed at the input-output pins DQ0 through DQ7. Next, the chip enable and write pins are taken high. When this occurs, the ready busy pin labeled R not B is brought low. When the write operation is completed, the ready busy control pin goes high to indicate the IC is no longer busy and can now be read or written to. The typical EEPROM can be erased and written to thousands of times and still maintain its reliability. EEPROMs are available in 8K, 64K, and 256K capacities. We will now pause for a short review of an electrically erasable, programmable, read-only memory device. The EEPROM is erased electrically and does not require the use of ultraviolet energy. The EEPROM can erase and overwrite portions of its memory. It does not require the entire memory to be erased first. EEPROMs use a floating gate technology which is very similar to that used by the EEPROM device. The EEPROM will generate its own programming voltages within the IC. This allows the EEPROM to be powered from a single 5-volt power source. EEPROMs can be erased and written to several thousand times without losing reliability. EEPROMs are commonly available in 8K, 64K, and 256K capacities. This concludes review number 4. Now we are going to examine RAM technology. This next portion of the video deals with random access memory, or RAM for short. All semiconductor RAM devices are volatile, which means that the device is unable to retain memory when the power source is removed. Even though a RAM device is volatile, it can be made to maintain its data for a given period of time. This period of time could range from minutes to weeks. To force the RAM device to retain its memory requires a backup power source, which is usually in the form of batteries. When RAM circuitry is supported with battery backup circuitry, it is often referred to as non-volatile RAM, or NVRAM for short. Most electronic processing systems will require at least some RAM. The amount of RAM required will depend upon the application for the system. There are two basic types of RAM, static and dynamic. Both types have particular benefits and drawbacks. We will examine them separately. We will begin by examining the static RAM first, since it is the oldest and most straightforward form of temporary semiconductor memory. Static RAM uses flip-flops to store individual bits of information. As you recall from Digital 2 of the UCanDo video series, the flip-flop is the most basic form of electronic memory element. The simplest of the flip-flop configurations is the RS, or latch flip-flop. It is constructed by crisscrossing the inputs and outputs from two NAND gates. For a more thorough understanding of how the flip-flop works, please refer to the Digital 2 video. Static RAMs are constructed with either bipolar or MOS transistors. The bipolar RAM cell is very fast, with typical access time of less than 50 nanoseconds. However, their primary disadvantage is that they dissipate relatively large amounts of power. 0.5 milliwatts per bit is not uncommon. This large power consumption is due to the flip-flop circuit, in which one transistor is always saturated. The MOS static RAM cell, on the other hand, produces a much lower power dissipation. Typical power dissipation for the MOS device is only about 0.15 milliwatts per bit. However, access time can typically take as long as 100 nanoseconds. The memory organization used within the static RAM is similar to that used in the read-only memory devices. As you can see, the static RAM uses a row selector section which also contains decoder circuitry, a column selector section which also contains decoder circuitry, data control and input-output control circuitry, and a memory array of semiconductor devices. Reading data from the RAM device is not a complex operation. First, the desired address is selected. Next, the chip enable input, not CE, is brought low. After a very short period of time, the data at the selected address will be present at the output. As you may have noticed, there is only one data output on this device. By simply paralleling the memory ICs, you can create a 4-bit or higher output memory device. By connecting the address and control lines in parallel, the same address in all ICs will be selected simultaneously. Since static RAM uses flip-flops to store each bit of information, and each flip-flop requires the use of 6 transistors to store a single data bit, there are design limits to the number of reliable transistors which can be manufactured on an IC chip. Also, as the static RAM gains size, the power consumption begins to grow, and the heat generated within the device will begin to affect the operation of the circuit. We will examine a more efficient RAM device later, but for now, we'll pause for a short review of the memory device just discussed. Random access memory devices are volatile, since they can only retain data when power is applied. Any loss of power will result in loss of data. Any static RAM device which uses a battery backup system is called a non-volatile or NVRAM device. The NVRAM device will retain its programmable information for short periods of time, days or weeks. The static RAM device uses flip-flops to store individual bits of information. The two major disadvantages of the static RAM device are, first, they dissipate too much power, and second, each flip-flop memory cell occupies a relatively large area on the IC, which limits the maximum number of cells available. Static RAM devices are available in both bipolar and MOS configurations. The bipolar is the faster of the two, but it consumes more power than does the MOS device. The MOS configuration, however, has a much slower operating speed. This concludes review number 5. Next, we will examine a RAM device which uses a completely different technology to accomplish data storage. Up until about a decade ago, electronic design engineers would avoid dynamic memory like the plague. Their reasoning was simple. The disadvantages far outweighed the advantages. The primary disadvantage was that dynamic RAM required a lot of support circuitry. It also required 3 supply voltages, and timing was most critical. But today things have changed. Today's inexpensive dynamic RAM devices are much easier to use and are capable of providing more memory for the dollar. Any circuit designer worth their salt must become familiar with this device. The key difference between static RAM and dynamic RAM is the technology used to store the data. As is shown here, each memory cell in a dynamic RAM device stores information as a charge on a capacitor connected to a single MOS transistor. Utilizing single transistor memory cells has accomplished 2 important objectives. 1, much more memory can now be placed in the IC, and 2, less power per bit will be consumed by the device. To write data into the memory cell, the data bit is placed on the bit line, then the cell is selected through the row or word select line. The capacitor then charges through the MOS transistor to the bit line voltage level. When the row select line turns off the MOS transistor, the capacitor will retain its charge, thereby storing the data bit. Due to the small size of the capacitor used to store the bit of information, the dynamic random access memory device must be updated frequently. The storage capacitor can only sustain its charge for a few milliseconds, therefore each memory location must be refreshed about every 2 milliseconds. If the cell is not refreshed, it will simply lose its data. Here you see a block diagram of the internal structure of a dynamic RAM device. Actually, it looks quite similar to the other memory devices already discussed. The primary difference in this device is its timing control and refresh logic control section. Notice there are 3 control inputs in this section. One is labeled RAS for row address strobe. One is labeled CAS for column address strobe. and the third is labeled W for Write Enable. There are several methods used to refresh the dynamic RAM device. The simplest method is called the RAS-only refresh. The RAS-only refresh method involves holding the CAS input high. When the CAS control input is held high, the output is placed in a high impedance state, which in effect disconnects the output from the data bus. The refresh circuitry then selects one row at a time, pulsing the row address strobe, low for each row as they are addressed. The sequence of the addressing doesn't matter, as long as each cell is refreshed in time. Another variation of the RAS-only refresh method is referred to as hidden refresh. When using the hidden refresh method, the CAS input is held at a logic low instead of a logic high, as was used in the RAS-only method. This allows the valid data to remain at the output while the rows are selected and refreshed. Depending upon the timing of the system, the CAS input may be held low for several microseconds, during which several rows may be refreshed. There are other variations of refresh methods, but these variations add a fair amount of complexity to the dynamic RAM IC. Fortunately, however, there are refresh controller ICs available for many different dynamic RAM sizes and configurations. Here you see the 29F68, which is a Fairchild Dynamic RAM Controller IC. Notice that this IC provides two 9-bit address inputs. Inputs AC0 through AC8 are used for the column addresses, and inputs AR0 through AR8 are used for the row addresses. The input labeled NOT CS is the chip select input. The outputs are labeled Q0 through Q8 and are capable of driving up to 88 dynamic RAM devices. The MSEL is the memory select input. The MSEL input is used to select between the row and column counter contained within the IC. The input labeled LE is the latch enable input, which is used to latch the row and column addresses. The select inputs are labeled SEL0 and SEL1. When the select inputs are used in conjunction with the memory select input, they are decoded to determine which row address strobe outputs and column address strobe outputs will be active. Inputs MC0 and MC1 are the memory cycle inputs. These inputs are used to control the operating mode of the IC. The next input is labeled NOT RASI, which is the row address strobe input. And NOT CASI is the column address strobe input. Pin NOT OE is the output enable. The pins labeled CAS0 through CAS3 are column address strobe outputs. And the pins labeled RAS0 through RAS3 are row address strobe outputs. The 29F68 Dynamic RAM Controller IC is designed to be used with 16K, 64K, or 256K dynamic RAMs. The two 9-bit addresses are used to store the row and column addresses provided by the processor, while the 2-bit latch from pins SEL0 and SEL1 are used to select one each of the 4 RAS and CAS outputs. In the refresh mode, 2 internal counters cycle through the refresh addresses. Only the row address is used for normal RAS-only refreshing, generating up to 512 addresses to refresh a 512 cycle refresh dynamic RAM. Let's review the most recent material we have discussed. The memory cells contained within the dynamic RAM device store information as a charge on a capacitor connected to a single metal oxide semiconductor transistor. Single transistor memory cells allow more memory to be placed on one chip. Single transistor memory cells also require less power per bit. Due to the small size of the capacitor used to store the single bit of data, the dynamic RAM device must be updated frequently. This updating sequence is called the refresh cycle. The most common refresh method is the RAS-only refresh. This allows one row to be refreshed at a time. The hidden refresh is another variation of the RAS-only refresh cycle. The primary difference is that the data remains valid at the output. Dynamic RAM devices are available with the refresh circuitry contained within the dynamic RAM IC. Separate dynamic RAM controller ICs are also available. This concludes review number 6. Next we will examine a mass storage system called magnetic bubble memory. One of the most promising memory devices designed in the past 2 decades is the magnetic bubble memory, or simply bubble memory as it is usually called. Bubble memories are so vastly different from the other semiconductor memory devices which we have previously examined that the best way to understand how they work is to discuss how they were discovered. In 1967, a scientist at Bell Telephone Laboratories discovered some very unusual effects in a thin wafer of magnetic garnet material. The thin magnetic garnet film contained magnetic domains which formed a maze-like structure. When a magnet was placed near the magnetic garnet material, the serpentine patterns would shrink into tiny cylinders, which when viewed on end would look like bubbles. These magnetic bubbles are about 5 micrometers in diameter and tend to drift in the thin layer of garnet. Like ordinary magnets, the magnetic bubbles will tend to repel one another. Since the bubbles repel one another, they maintain a certain distance between each bubble. This makes them suitable for use in a memory system. Now that you have a basic concept of what a magnetic bubble is, let's examine how these bubbles can be used to store data. We will begin by examining how the bubble memory device is fabricated. First, a non-magnetic crystal substrate like gadolinium gallium garnet is placed in an oven. Then a film of magnetic material like yttrium iron garnet is grown epitaxially on the crystal substrate. Next, a thin layer of silicon oxide is deposited on top of the YIG layer. Then a pattern of permanent magnetic material is deposited on the silicon oxide. The pattern resembles that of a T and bar configuration. Next, the chip is sandwiched between 2 permanent magnets which provide a field that points the opposite way from the bubbles. This causes the bubbles to form in the garnet material. The bubbles are moved by applying an additional rotating magnetic field that is parallel to the plane of the film. The rotating field is generated by 2 coils perpendicular to each other carrying sine wave or triangular wave currents that are 90 degrees out of phase with each other. Bubble movement is controlled by the pattern of permanent magnetic material that was deposited on the magnetic garnet film. Now let's see how the bubble is moved. As the rotating magnetic field moves, it causes the molecules within the permanent magnetic material to align with the field. Each bubble will move to seek the nearest north pole of a segment. The T-bar configuration will keep the bubbles separated, so there is only 1 bubble per segment. The presence of a bubble indicates a 1, and the absence of a bubble indicates a 0. Each time the field makes 1 complete revolution, all the bubbles will have advanced 1 step. As you can see, this type of memory works like a shift register, whose shifting frequency is determined by the frequency of the rotating magnetic field. Bubbles can be moved at the rate of 10 million steps per second. Internally, the bubble device is organized with a major and minor loop organization. The major loop is used to control the data stored in each of the minor loops. The major loop is also used to transfer data from a minor loop into the output or to take bubbles created by the bubble generator and store them into a minor loop. The minor loops, of course, are used to store the data. To write information into the bubble device, the data is placed serially into the input pin. The input pin is connected to a special bubble generator structure contained within the IC. The bubbles are transferred in the major loop until the entire program has been loaded. At that time, the transfer input is activated, which causes special transfer gates to download the data from the major loop into a vacant minor loop area of the IC. The average data stored in a single minor loop is 640 bits. To read information placed in a bubble device, the transfer input is once again activated and the data in the selected minor loop is loaded into the major loop. Once the data is in the major loop, the bubbles are sent through the replicator section of the IC. At this point, one of two things will happen to the bubbles. If it is a destructive read operation, as shown here, the data will be read, then the bubbles will be erased by applying an opposite polarity magnetic field to the bubble in the bubble annihilator section of the device. Or if it is a non-destructive read operation, the bubbles will become stretched, then split in two by the replicator current. One bubble is then sent to the output, and the other bubble is circulated in the major loop. The output contains a detector section which has sufficient sensitivity to detect the signal produced by the presence of a magnetized bubble. Bubble memories are non-volatile, but their size, speed, and available memory have limited their use to only a few applications. Still, their potential for storing millions of bits of data make them a viable alternative to other mass storage devices. We will now look at a brief review of our discussion of magnetic bubble memory devices. Bubble devices store data in the form of magnetic particles called bubbles which float in garnet material. The presence of a bubble indicates a 1, and the absence of a bubble indicates a 0. Bubble movement is controlled by two rotating magnetic fields that are perpendicular to one another, and each carries a sine or triangular wave current which is 90 degrees out of phase. The operation of the bubble memory is very similar to a shift register whose shifting frequency is determined by the frequency of the rotating magnetic field. Internally, the bubble device uses major and minor loop organizations. The major loop is used for read and write operations, and minor loops are used to store the data. This concludes this video on memory devices. As with all UCanDo videos, it is recommended that you view it often. Remember, in today's technology, the best jobs go to those who are best prepared.